that you will be possibly using, and I give you a multiple size, decision size function given by this, then you pick now your multiple decision functions according to this thing, delta m, am, del alpha. Okay, so for each of the m, you compute am at alpha, and then that's how you pick your decision function. That's your multiple decision function. Now, when you do this, okay, when you pick your decision function in this way, then you have what you call as you usually call it as the weak family-wise error rate. The weak family-wise error rate is the probability, or this R sub 0, when this P has such that all the genes are not significant. Okay, so you call that as the weak family-wise error rate. And then this one turns out to be equal to this. And then that's, of course, less than or equal to alpha by the constraint that we had put on those size functions. Okay? Now, so now we have the Niemann-Person paradigm for m is equal to 1. But we want to use that same thing when m is now large. How do we do that? So same problem. I'm going to control now my R sub 0 to be less than or equal to Q. That's one type of error. Or control R sub 1, which is the FDR rate, the false discovery rate, to be less than or equal to Q. For P, that such that all the thetas of m are equal to 0. This is not yet the most practical one, because we know that that will not be the case. Okay, but this is the beginning of the solution. Okay, so we control this. And then when you have strong control, on the other hand, by the way, that's weak control. When you have strong control, you would like to do that for whatever P is. Okay, whatever P is, you would like to have that control. But that's the more difficult problem. But the solution to this problem turns out to be tied in to the solution to the weak problem. Okay, now, if you do this control, what you would like to do then is to make this as small as possible. That is the type 2 error that we have. But that is the type 2 error that is now measured with respect to that multiple decision action that we are making. Okay, so it's the same principle. Okay, control type 1, minimize type 2. Okay, so that's the same principle that we are using there. Now, so this is just kind of a way to show you how the idea is, okay? And the idea is that I could calculate for you this R sub 0, and that is given by this one here, okay? If I know these thetas of m here, the thetas of m are the three states, okay? If I know them, then I could actually come up with an alpha that will make this less than or equal to Q, the control that I would like to have. If I know this one. If Paul is alive, then I could ask him what the thetas of m's are, and then I could then determine for you the alpha that I should be using. Okay? So that's the problem with that, because that involves thetas of m. And we could do that. But the problem is that we don't have that. Okay, so I call this as Oracle Paul's choice. Okay? If we know the thetas of m, I could get you the best alpha that you should be using to pick out your test. And that is given by this formula. But the problem there is that it depends on thetas of m. I know these functions because I input that, okay? Although, well, later on I could tell you how to choose these particular ones to optimize. But this thing though, it still depends on the true states of the thetas of m, which I don't know, because we do not know P, okay? So I call that as Oracle Poles. If we have an oracle, then we actually know the truth and we know how to do that, okay? So, now, but a simple solution to that is to estimate the thetas of m. How do we estimate that? Remember, the deltas of m are actually the ones that will give you your action, 0 or 1. So I could use this now here to estimate my thetas of m. Okay? It's either a 0 or 1 function. Okay? Decide that's discovery or not based on this thing. And then I could plug that in there, and then that will solve the problem. So now I have this oracle's choice in some sense, or estimated by this quantity. And now everything there is known to me. I could compute that. Of course, the computation is still complicated, but it could be done because it could actually be converted to a simple formula in that situation. But this is how we come up with that alpha that you have there. So here's the chosen multiple decision function then is going to be given by this. Okay, the deltas of m evaluated at the a's of m evaluated at that alpha dagger that I had shown you. So give me the data. I give you this, then I come up, and then I make it a decision. Okay? Now, here's the theorem for this particular case. Given a delta, in A, this is the multiple size function, the delta dagger Q defined above has control of the type 1 error. Okay? But it need not yet optimize the type 2 error. But at least it controls for you the type 1 error rate in that situation. In that case, the family-wise error rate, because this is just for R sub 0. Okay? Now, this also shows you, by the way, that this is for strong FWER control. Even though I do not know P, I still guarantee you that this is going to be less than or equal to Q. So the procedure is adapting to the situation. We don't know P, but I still am able to control for you the probability, the family-wise error rate. Okay, and that's an important thing because it's not only we control, but it was actually derived based on the solution for the weak FWER control. Okay, so now you could convert all of this, by the way, to generalized p-values. Okay, remember the p-value in one-dimensional testing? It is the smallest alpha value that you could have to reject the hypothesis. Okay, you could also derive, come up here with what you call as a generalized p-value, and that is the smallest alpha that you should use to get you a decision of discovery for the M problem. Okay, so it's just the same notion that we had there. Okay, and then you could order that and so on and so forth. No need for that thing there. And then this is for the purpose of coming up with the other control, which is the false discovery rate. If you do this, okay, you could obtain a formula for the false discovery rate, and that is given by this. Okay, but you don't know that because you do not know theta sub m, and then you do not know p. But again, you could come up with a heuristic here and observe that this expectation is less than or equal to this, and then you come up with an alpha star, which is given by this formula. It's the largest alpha such that it satisfies this condition. The delta sub m there, of course, is data dependent. So this is the largest alpha that you could satisfy this. When you use now an alpha star of this form, and then you pick out your decision functions using this alpha star, then you get FDR control. Okay, and this is now the goal that Benjamini Hochberg has, okay, which is to control the FDR. But you could actually obtain that using this general framework, and then you get the result here that the R1 delta star alpha, okay, Q is going to be less than or equal to Q, whatever P is. So strong FDR control, essentially. Okay, now, so you might be familiar with the Benjamini Hochberg, which I'll just flash here. But that is a special case of this procedure, actually. Okay, well, I will show it. Okay, so you have this situation. So here you have a class of strong FWR controlling MDFs that's given by this first one. And then you have here a class of FDR controlling MDFs that's given by the second set that you have there. And then CDAC sequential step-down strong FWR controlling belongs actually to this one, while the Benjamini Hochberg belongs to the second class. So the get recovered, these are the two popular methods for controlling FWER and FDR, and they are just one element in that general thing there. Okay, so, okay. Now, just to mention, by the way, this is the FDR, or the Benjamini Hochberg procedure. In the Benjamini Hochberg procedure, okay, very simple to use. What you do is you take the ordered p-values. These are the p-values that you obtain, and then you order them, and then you take this capital K to be the largest K that satisfies this condition. Okay, so it's very easy to implement in R, for instance, or you could also have a package in the R thing there, but you take that, and then your decision function is given by this thing. You decide discovery if the p-value for the M test is less than or equal to P parenthesis K, where K is given by this. This is data dependent, of course. These are based on the data. So that's the Benjamini Hochberg procedure. But the question that we had there is that actually the best? And it turns out that it's not the best in the certain situation. Okay. Okay. How many minutes do I have? So to decide where to cut here. 5 minutes. 5 minutes. Okay. Okay. Now here's an example, for instance, of an application of the Benjamini Hochberg. This is the data, and I took there the data with only 2 groups. And if I apply the Benjamini Hochberg there, I get about 2,600 significant genes. Okay. So of course you go through that, And then this, for instance, the p-values for the 42,000 genes, okay? That you see, you notice the bumpter. I could explain that, but I don't have time to explain that bumpter. But generally speaking, if all the genes are not significant, then you would expect that this will be a flat one. These p-values here are the ones that are actually referring to significance. And in the Benjamin-Hochberg, we try to pick that out. Okay, and if you had chosen those genes, you could possibly choose also a smaller number. And these are, for instance, the plots of the means for the two groups. And then the blue ones, they are the ones that got picked out to be significant. And then the red ones are the ones that we actually analyzed further. But you could do those types of analysis after you have decided on which genes are important in that particular case. You could then do some clustering, for instance. Okay, this is the heat map of the selected ones. You notice, of course, the separation between the groups. But that's from the practical point of view. And then the biologist or the medical person will then have to go to the genes and then analyze each of those. And here's a clustering of the genes that we actually found out to be significant. Okay, so now this is the part though that is new to the whole thing. And the problem that comes up there is this: could we improve the Benjamin-Hochberg procedure? Okay, see, one thing about the Benjamin-Hochberg procedure is that it does not take into account the powers of the individual tests. It only uses the p-values. But Niemann in person, in their paper, said power is germane to the whole problem of optimization. If you're going to come up with the best procedure for decision making, you need to look into the possibilities, the other possibilities. But Benjamin-Hochberg, a lot of the procedures that we currently have don't take that into account. We forget about the power. Where does the power come in? Why are there differences in power? It could be because there are different effect sizes. It could be because a variance in one gene is bigger than a variance in another gene, and it changes the effect size that you have. In sample size determination, effect size is an important component. But we ignore that in this particular case. And so this is the problem that we ask in this situation: could we improve these things here? And it turns out that you could actually improve the procedure by taking into account the power. And here's the basic idea without going into detail here. You have the power functions. The power functions get into R2. That's the second risk function. You could then try to minimize that function subject to the constraint that you have on the type 1 error probability. Okay? So, and then you get your optimal alpha. When you do that, then you come up with the optimal size that you need. And then you get a better procedure that will minimize your type 2 error probability with control of the type 1 error probability. And this is the problem that we have here. And then you could actually do that from the result that we had. And this is just the thing there. And it's the solution depends on this mapping. This is the map from alpha into the power. And this map actually is what we refer to as the receiver operating characteristic curve. Those are the receiver operating characteristic curve, and that's the one that determines for you how to optimize in that situation. And then I mentioned here that the exchangeability assumption that we usually do for Benjamin-Hochberg is more the exception rather than the rule, because there will be differences in the effect sizes or the powers of each of these individual tests. It's possible that in one gene you are using a chi-square test, in another one you're using an up test. Okay, so different possibilities in that case there. Okay, so this is the situation. Here's the theorem that I just wanted you to see. The optimal decision is obtained from this formula.